Hello everyone, welcome to lesson number 22 for BC Calculus. This is a lesson on optimization, and really what optimization is an application on how to find max and min. So in lesson number 20 we talked about how to find max and mins algebraically on functions. Well, now let's actually use it in the real world. So we're going to go ahead and start with example number 1, the most classic example for an optimization, where it says find the maximum volume of an open top box created from a 20 centimeter square sheet of paper. And so what they show you here is an actual 20 centimeter square, and you can see how they're going to cut the corners of your box right here, right? Some distance height. And so when you cut them, you're going to fold them up and you're going to create yourself a box. So notice that it is a top, the box is open top. So I am not remotely good at drawing here, but really we just have a box that's going to look like this, where the top is open. And so this little piece right here, this little distance right here, is going to be this distance right here. So actually let's change the color for you. So this distance right here is going to be the distance of this. So you guys can kind of visualize what's going on here when we fold these things. Not that you need to. I'm going to show you the calculus in a second. But just to get an idea, so this is going to be that distance right there. And then the point of this is that this right here, this is going to be that distance right there. Right? So if you guys can just visualize this, and you can actually take a square, cut it out, and fold it, and you're going to see what I'm seeing right here. So what we've just done here is we have created ourselves a length, a width, and a height. And you can now figure out what these distances are based on this little not so great picture that I've drawn right here, but you can see what it is. So in order to find a maximized volume, there's a couple things. Well, this is all derivatives. So everything, the first thing I'm going to say right now is that when you're doing optimization, you are going to do derivatives. So this is an application for a derivative. So these are derivatives. Now, one of the strategies that you need to do here is you need to get everything in terms of one variable. That's really, really, really important. So everything needs to be in terms of one variable. So let's do that first. So let's go ahead and rewrite these problems, or these dimensions, in one variable. So I'm going to go ahead and call my height equal to x. Okay, so my height's going to be equal to x. So that's my height. Now my length, which is going to be this guy right here, is going to be equal to, so the whole thing is 20, remember, but I'm taking out this h and this h. So this length is going to be 20 minus 2h, which we now can just say that that's going to be 20 minus 2x. And so width is going to be this distance. Well, it's the same thing as this, right? We're looking at a square. So this is going to be 20 minus 2h, which again is going to be 20 minus 2x. Now, once we realize that we have our dimensions and we have everything in terms of one variable, then we need to actually, this is kind of like what we did with related rates. We have to find an equation to solve for here. And so we're not doing related rates, so someone said, because everything's in one variable, but we do want to find the volume of this shape. Well, this is again it's actually kind of a cube. It's like a rectangular prism, right? Because the top's not, so it's actually going to be a rectangular prism. So it's just the volume is equal to the length times the width times the height. You guys all know that. And so let's go ahead and substitute in. So volume is going to be equal to the length. Well, the length is going to be 20 minus 2x. The width is going to be 20 minus 2x. And the height is going to be x. And so now, ladies and gentlemen, we were able to do two really awesome things. One, we were able to get our kind of an expression for the volume of this particular box. And then more importantly, in terms of one variable. So before we actually start the problem, we're just going to go ahead and simplify this a little bit better by foiling what you see here. And so you're going to get 4x squared, you're going to get minus 80x, and then you're going to get plus 400. And then we're going to get that the volume is going to be equal to 4x cubed minus 80x squared plus 400x. Okay? So that's going to be the equation that represents the volume of this rectangular prism. So this gives us what our volume is. But we want to optimize it. We want to know what is the best dimensions that we can do to make this box optimize. So what we're going to do first, and like I said before, is we're going to take the derivative of this function. So we're going to take the derivative of v, all right, in terms of x, okay? It's all in terms of x, so again, we don't have to worry about too much related rates. So we're going to get 12x squared minus 160x plus 400. Now this ends up becoming a pretty big number, right? Pretty big number here. So, you know, calculator would be helpful here, but we can actually factor out a 4. I mean, that does help us, you know, slightly with this. And then we do want to factor this. So what you want to do now is you want to find your derivative and you want to set equal to 0. So I should have actually said that at the beginning. So once you have your general expression in terms of one variable, then you want to find the derivative of that and then set it equal to 0. So I want to factor this problem, and you know, we chose numbers that made more sense, so that's why this ends up being a little bit crazy, but this does actually factor down for us like so. So you can see that 3x squared, and then I got minus 30x minus 10x is negative 40x plus 100. So I get that x is equal to 10 over 3, and that 10x is equal to 10. All right, remember that this represents the height. This represents the height of the box. So which one of these will give us the maximum volume of this, 10/3 or 10? Well, this goes back now to what we did in the previous lesson, or actually lesson number 20. We can looking at velocity, or our volume, excuse me, here. We're going to go ahead and plug in 10 over 3 and 10, and we're going to look at our sign. So what's our values? Are they high, they're low, are they increasing, or are they decreasing? Because really what's happening here is, are they increasing or decreasing at this time? So if we plug back into your derivative, so plug in here, so something, again, this is a good thing for, you know, a calculator. If I plug in 0, if I plug in, let's not plug in 0. If I plug in 0, I'm going to get a positive number. That's actually a really easy way to do this problem. If this were a non-calculator question, clearly 0, this cancels out unless 400. These are not double roots. So you know this is going to be negative and this is going to be positive. So you can plug in something like 5, you know, something in between 10/3 and 10, and say that this end up would be a negative value. And then, you know, because again, the negative 160 here. And then something like 11, you can see that this is going to be positive. So again, previous lesson, we talked about that if my function's increasing, that just means that my volume is getting larger here, all right? And then it's getting smaller, and it's going to get bigger again. So you guys can see that I'm looking for the absolute maximum. So I'm looking for the maximum here. So the value that I want, the height that I want is 10 over 3. So I can now say that based on this problem and these dimensions, that when my height is at 10 over 3 centimeters, my volume of this box is going to be optimized. So now, what is that volume, right? We want to figure out, because it says find the maximum volume. So this is the height. So all I have to do now, ladies and gentlemen, is take my volume and plug in 10 over 3 to our value, right? And so really, this could be rewritten as x times 20 minus 2x quantity squared. But again, you can use your calculator for this. I encourage you to do so. And that's what I'm doing right now, is using my calculator, and I'm going to get that it's going to be, the volume is going to have the dimensions of this. So this is the volume this is the optimal volume that we can have that's going to hold. So there we go. So guys, I'm going to just end the video for this one. I feel like for optimization, it's just easier maybe to do one question at a time, just to do videos split up. So this is called the box question video. So we'll come back into the next video where I talk about surface area and volume. So hopefully this made sense to you guys. But again, optimization really is to find the equation, put it in one variable, find the derivative, set it equals 0, and then figure out where the maximum min is, and then just go ahead and plug it back in. So I will see you guys in the next video.